Hello students, today we will look at applications of derivatives chapter 7 of the TN Tamil Nadu 12th board maths syllabus. So we look at exercise 7.8, some of the important questions which have to do with like optimization problems. Before that, let us look at some concepts which will be used in this exercise. So this theorem which deals with the first derivative test. Let c, f of c be a critical point of function f of x that is continuous on an open interval I containing c. If f of x is differentiable on the interval except possibly at c, then f of c can be classified as follows. When moving across the interval from left to right, if f prime of x changes from negative to positive at c, then f of x has a local minimum f of c. If f prime of x changes from positive to negative at c, then f of x has a local maximum f of c. If f prime of x is positive on both sides of c or negative on both sides of c, then f of c is neither a local minimum nor a local maximum. So here, what this means is, suppose we look at this graph, a local maximum happens, c1 is a point which is a local maximum. So to the left side of this c1, we have f prime of x is a positive value, whereas to the right side of c1, f prime of x is a negative value. So that means this c1 point is a local maximum. Similarly, if you consider at c2, to the left side of c2, we have the slope is decreasing and it's negative. To the right side of c3, we have positive. So this point is a local minimum. So this test maybe looks a bit more complex. So we will use the next test for the optimization problems. That is the second derivative test. Suppose that c is a critical point at which f prime of c is equal to 0, that f dash of x exists in the neighborhood of c, and that f double dash of c exists. So then f has a relative maximum at c if f double dash c is less than 0, and the relative minimum at c if f double dash c greater than 0. If f double dash c is equal to 0, the test is non-informative. So this basically says that we find the critical points, that is either the minimum or a maximum point, by doing the first differentiation and equate that to 0. And to find if it's the maximum value, we do the double differentiation. So f prime of c, f double dash c less than 0, what it means is that it is a concave downward curve. So in a concave downward curve, this looks as a maximum value. For if f double dash c is greater than 0, it's a concave upward curve. So f prime of c equal to 0 is a minimum value. So using this, we'll solve the problems. So for optimization problems, this is the steps given in the textbook. That the procedure is draw appropriate figure and label the quantities relevant to the problem. Then find an expression for the quantity to be maximized or minimized. Using the given conditions of the problem, the quantity to be extremized. Then we determine the interval of possible values for this variable from the conditions given in the problem. And then we use the techniques, that is absolute, extremum, second derivative test, to get the maximum or minimum. So based on this, we'll approach this exercise here. So we'll be dealing with question number 3 and question number 5 and then question number 12. Question number 3 is find smallest possible value of x square plus y square given that x plus y equal to 10. So the solution is that we define a function x square plus y square. So we need to maximize this function given x plus y equal to 10. Now I am rewriting this function only in terms of x. So x is x square, y is 10 minus x. So we have this expression x square plus 10 minus x the whole square. Now we apply the first order differentiation, that is df by dx gives us 2x plus 2 into 10 minus x into minus 1. So this gives us 2x plus 2x minus 20, which is 4x minus 20. So here to get the critical point, we apply f prime of x equal to 0, which gives us 4x minus 20 equal to 0, and then x equal to 5. Now we have to verify look at the double differentiation. So if we double differentiate f prime of x, 20 becomes 0, 4x if we differentiate we get 4. So we have 4 which is greater than 0. So what we know from the second derivative test is that if 4 is the second order differentiation is greater than 0, it is a concave upward curve and we have the minima point. So x equal to 5 gives us the minima point, and the corresponding value of y is 10 minus x equal to 5. So minimum value of f is x square plus y square, which is 50. Now to give a visual representation of this, what we are trying to do is, this is not required for the solution, but I'm just showing this for sake of illustration, that x plus y equal to 10 basically defines a straight line in the xy plane with x-intercept as 10, y-intercept as 10. Then x square plus y square is basically the radius of a circle centered at 0. So if we have to minimize that value, see even this circle, the outer circle that has points on these two lines, but that value is higher. So the smallest possible value is obtained when this circle is tangent. In this circle, it is drawn such that this line is tangent to it. So that is what is given by this solution. Now the next question is, a rectangular page is to contain 24 centimeters square of print. The margins at top and bottom of page are 1.5, and margins at other sides of pages 1 centimeter. What should be the dimensions so that area of paper used is minimum? So here we have to first draw the diagram. So we have the page over here. Its left and right margins as 1 and 1. Whereas top and bottom margins are 1.5 and 1.5. So we let x be the width of the paper and y be the height of the paper. So the printed portion is the shaded portion given by x minus 2 into, which is the horizontal portion, and then the vertical portion is y minus 1.5 into 2, which is y minus 3. So it is given in the problem that the printed portion is 24. Now the paper area is x into y. Now I am going to write the area just in terms of x. So using this first relation, we have y minus 3 is equal to 24 divided by x minus 2. Therefore, y is equal to 24 by x minus 2 plus 3. Therefore, area in terms of one variable x is x into this expression, which when we simplify gives us 24 plus 3x minus 6, the whole divided by x minus 2. So this gives us x into 3x plus 18 divided by x minus 2 which gives us 3x into x plus 6 divided by x minus 2. Now we have to get to the first differentiation here. So the first differentiation that gives us, we have to equate it to 0 to get the critical point. So the numerator is 3x squared plus 18x. The denominator is x minus 2. So we know this formula for the division formula for d by dx. That is u by v when we differentiate is u prime v minus uv prime divided by v square. So here if you do u prime, we get 6x plus 18. When you do v prime, we get 1. So dA by dx is this value into this value, this into this, minus this into this, the whole divided by v square. So what we have here is, finally while simplifying it, 3x square minus 12x minus 36. And taking 3 out common here, I have x square minus 4x minus 12. Now I'm going to factorize this numerator. Yes, so we know that the product gives us minus 12, the sum gives us minus 4. So that is satisfied by minus 6x and plus 2x. The final expression becomes x plus 2 into x minus 6 divided by x minus 2 the whole square. So for this to be 0, we have the numerator equal to 0. So either x equal to minus 2 or 6. Now x equal to minus 2 is not possible. So x equal to 6 is the answer. Now we are going to apply double differentiation. So we have dA by dx as given as this value. Again, we'll use the differentiation rule on divided functions, that is u by v. So I find u prime over here, which is 2x minus 4, and then v prime is 2 into x minus 2, which is 2x minus 4. So I'll multiply u prime into v minus v prime into u. While simplifying, what we get is x minus 2 the whole square minus x square minus 4x minus 12. So when we simplify, what we get is x square and x square they cancel, minus 4x and 4x cancels. And finally we have 6 into 16 divided by x minus 2 the whole cube. At x equal to 6, when we substitute, we get this as a positive number. Therefore, we prove that x equal to 6 is a minima point. Now to find the corresponding y value, I will write this as y equal to 24 by x minus 2 plus 3. So what I basically get is 6 plus 3, which is 9. I hope you understood the logic behind how we solve this. So the dimensions of the page finally is 6 centimeter into 9 centimeter. It is this 6 and this is 9 centimeter. Now there's an alternate way of solving this problem, which will give us an easier expression to deal with. That is, I choose the shape. I choose the printed area width as x and the printed area height as y. So that is xy equal to 24. And then the area of the paper will be x plus 2 on the horizontal, and vertical will be y plus 3. So we have xy plus 2y plus 3x, which gives us 30 plus 2y plus 3x. And from this expression, we can write y as 24 by x. So this we can solve, and this is an easier way to get the solution for the same problem. Now we have to, so the next question which we look here is question number 12. A hollow cone with base radius A and height B is placed on a table. Show that the volume of the largest cylinder that can be hidden underneath is 4 by 9 times volume of cone. So for this problem, we have to use some geometry which we have learned in lower classes. That is, suppose this is the cone with base A and height B. Now, there are different possibilities of keeping a cylinder there. For example, we can have a cylinder which is of very small height but a very wide radius. The other end is that we have a cylinder with very tall height and very small radius. And then we have something in between that is um, that is of an average height and average radius. So we have to maximize the volume of this cylinder here. Now, if we have volume of cone, we know is 1 by 3 pi into radius square into height, pi a square b, which is a constant. And the volume of the cylinder is b equal to pi r square h. So now what I'm going to do is try to get a relation between r and h, so that we have so that we can write the volume as a function of a single variable. Now, if you take a cross section of this cone and cylinder, what we get is a triangle for the cone and a rectangle for the cylinder. And in this triangle, we see that triangle CDB and triangle AOB, if we consider, then both of them, they have a 90 degrees here, and both of them, they have a common angle, which is B here. So we know from the theory of similar triangles that triangle CDB is similar to triangle AOB. So then we can write CD divided by AO, that is the corresponding sides. When we divide, they are the same ratio. So CD divided by AO, that gives us DB divided by OB. So we have the similar triangles formula which we are using here. And DB we can write as, is A minus R here. And OB is A. Similarly, CD is H and AO is B, height of the cone. So we rewrite this here and take B to the RHS, and I can write H as B into 1 minus R by A. The next step is to write the volume of the cone. So volume of the cone is pi R square H, and H we know is B into 1 minus RA. So we have pi into B, which is a constant, and R square minus R cube by A. Here it's not visible, but this is actually R cube by A. So when we differentiate, we have pi B constant value that comes out. And then when we differentiate R square, we get 2R. We differentiate R cube, we get 3R square by A for the extremum. So we have to solve this quadratic equation. R into 2 minus 3R by A equal to 0. Now either R is equal to 0 or this function, this expression holds true. Now radius of the cylinder cannot be 0. So we have to discard this solution. So when I solve for this equation, what I have is R equal to 2A by 3. R is radius of the cylinder is 2A by 3. Now to verify that this is the maximum, we have to do the double differentiation. So I will apply d square V by dr square, which gives me pi b into 2 minus 6R by 8. Now I substitute R equal to 2A by 3 over here. So what I get is d square V by dr square is pi b into 2 minus 6 by A into 2A by 3. So I cancel out A over here, and I get minus 4, it is minus 2 pi b. As b is a positive number, this is less than 0. So a negative value means it's a concave downward curve. So r equal to 2a by 3 gives the local maximum. Now the maximum volume, that is what is asked in the question. So r equal to, we just substitute 2a by 3 in this expression, v equal to vr. So what I get is pi v over here, 2a by 3 the whole square minus 2a by 3 the whole cube into 1 by a. So we take out a square to be common, pi b a square, and this one gives 2 by 3 the whole square is 4 by 9, 2 by 3 the whole cube is 8 by 27. And yeah, so first we do this as 12 minus 8 divided by 27 gives us 4 by 27. So the volume of the largest cylinder is 4 by 27 into pi b a square. And we know the volume of the cone is 1 by 3 pi b a square. So when we simplify, we get 4 by 9. So we have proved what was asked in the question using the theory of differential calculus. I hope you enjoyed and understood the problems in this exercise. We'll continue to other exercises in this chapter. உங்களுக்கு எக்ஸ்பிளனேஷன் தமிழில் வேணா சொல்லுங்க, அதுக்கேற்ற மாதிரி நான் தமிழில் உங்களுக்கு எக்ஸ்பிளனேஷன் கொடுக்குறேன். தேங்க்யூ ஃபார்